Thank you, Fran, for the introduction. So, in this talk, this is a joint work with this great team. We have Salvatore Oliviero, Lennart Bitter, Jens Eisert, Vittorio Giovannetti, Ludovico Lami, Lorenzo Leone, and my twin brother, Antonio Anna Mele. And in this talk, I will discuss quantum state tomography of optical systems. So quantum state tomography basically means learning unknown quantum states, while optical systems are a quantum system associated with infinite-dimensional Hilbert spaces. And the topic of quantum state tomography is really studied in the quantum optical setting. Indeed, also the term tomography was introduced in the quantum physics literature, specifically in the context of optical systems at the beginning, back more than 30 years ago. And tomography algorithms are a daily routine in optical labs, in quantum optical labs. However, in the last 10 years or so, quantum state tomography was studied also by the computer science point of view, in the finite-dimensional setting. An analysis of like sample complexity was done for the finite-dimensional setting, but in the literature of continuous variable systems, quantum optics, this was not done. And so despite there are many heuristic approaches validated in quantum optical labs, the literature of quantum optics lacks rigorous performance guarantees in tomography. And our work try to fill this gap. And this is the outline of the talk. I will first give an introduction to the problem of quantum state tomography. Then I will explain what is a bosonic system. During this talk, I will sometimes say the word bosonic systems or continuous variable systems, or also optical system. I mean, it's always the same thing. Then in the third part, I will talk about our results on quantum state tomography of bosonic systems. So quantum state tomography is the task of learning an unknown quantum state. You can imagine that you have an experiment, you run this experiment, and the output is a quantum system initialized in an unknown quantum state rho. And the task of a tomography algorithm is to learn to provide a classical description of an approximation of this quantum state by having access to many copies of the unknown quantum state. So the tomography algorithm takes in input, let's say, n copies of the known quantum state, and it outputs a classical description rho tilde that is a good approximation of the known true state rho. And in order to define, now let us mathematically define what does it mean good approximation. We use to measure the error in the approximation, we use the trace distance, because it's the most meaningful distance for distinguishing quantum states due to its operational meaning, the Oliver-Elstrom theorem. And so we say that basically the trace distance between rho tilde and the true state rho is smaller than parameter epsilon. But then there is also the parameter delta, that is the failure probability of the algorithm. This is because the tomography algorithm, any quantum measurement is the outcome of any quantum measurement are inherently probabilistic. So the output of a tomography algorithm is not deterministic. It follows a probability distribution. And what we require for a tomography algorithm is that the probability that the trace distance is small, the trace distance error is small, is large. That this probability is large, and the delta is the failure probability. We can imagine this in this talk that both epsilon and delta are a very small parameter. And the tomography algorithm is designed for learning states from a specific subset of the full set of quantum states. And this is if you have prior information of your state. For example, if you say that your state, if you don't have any information, you just say that S is the full state of all the quantum states. Or maybe if you have the prior information that your state is a Gaussian state or stabilizer states, this is the set, for example, of Gaussian states. Okay. So the problem, to summarize.
Are you considering CV states?
Yeah. Okay. Here I'm doing I'm explaining the problem of quantum state tomography in general.
Yeah, but then, assume that you have a finite-dimensional quantum system.
Yeah.
Do you at least get to know what's the dimension of it, or is it?
Oh, okay. Yeah. I am.
If you don't know the dimension, I wonder.
Okay. I think that one always assumes that it knows what is the. What is the quantum systems? At least, for example, it knows
the dimension. You mean?
Yeah, the
dimension.
dimension.
That you always know it.
Yeah. Yes, the dimension you always know it. And to summarize, the problem of quantum state tomography is the following. Given n copies of the known state rho contained in the prior assumption set, S, the goal is to output a classical description rho tilde such that it satisfies this relation. And now you can imagine that the experiment, running the experiment is expensive. So you want to minimize the number of state copies, n. And this is the definition of the performance of the tomography. So we define the sample complexity as the minimum number of state copies that satisfies problem one. And this is the definition of sample complexity, is the optimal number and that allows you to achieve the performance epsilon trace distance error and delta failure probability. So let's give some example of results known in the finite-dimensional setting. For example, if you don't have any prior information about your state, if your state is, if your unknown state is a arbitrary qudit state of dimension d, then the sample complexity is of the order of d square over epsilon square. And this is I'm using the theta tilde notation. I'm not going into the detail here to define it, but just saying that it is asymptotic behavior when both d and when d is larger and epsilon is small, is the relevant term in the.
Where the delta doesn't come into picture anymore.
Sorry.
Yeah, there's like a log 1 over delta hidden in the tilde.
Okay.
There is the delta. Yeah, it's always the dependence of that delta is always like logarithm of 1 over delta. I'm not writing it explicitly, but it's always like that, the dependence of the sample complexity. And I'm using this theta notation quite informally in this talk. Okay, then if you have more prior information on your state, for example, if you say that your state is pure, the sample complexity reduces, goes from d squared to d. And now let's give another example. For example, if you know that your state is a qudit state with rank at most r, you can say that the sample complexity is d times r. So in this case interpolates example 1 and example 2. And okay, now let's see what is a bosonic system. We are talking about quantum optical systems. So laser, beam splitter, basically the role that is played by one qubit or one qudit in the bosonic setting is played by the so-called one mode. You can imagine one mode has one qudit with infinite dimension. Basically, the Hilbert space of one mode is the span of 0, 1, 2, and for all the natural number. And these states of the compression of the basis are called the Fock states, and are the states with that represents the photons in your mode. For example, 0 is the state with 0 photon, the vacuum state. Then 1 is the single photon state, and then D is the state with D photons. And okay, this is the Hilbert space of one mode. Here, a bosonic system is a system that consists of n modes. So basically, we have like n qudits. Each of them has d equal infinite. And okay, we are interested in the dependence of the scaling with n in the number of modes. As in the qubit setting, one is interested in the scaling with the number of qubits. Here, we are interested in the scaling with the number of modes. Okay, in the examples before, n, it's like if you have a system of n qubits, it's like to have d equal 2 to the power of n. So all these scaling are exponentially in the number of qubits. So this is why tomography is inefficient. Okay, when it's okay. So tomography is inefficient. In general, it's an efficient problem for if you have not if you have prior information about the unknown states. And okay, so we have now let's go to topic of quantum state tomography of bosonic systems. Okay, a first observation is that without any additional prior assumption, tomography is impossible. The dimension of the Hilbert space is infinite. However, in lab, you have a prior information for sure. For example, you know that when you turn on your laser, the energy of the radiation is, for example, for sure less than the energy of the sun, for example. So you have prior information of your state. So in lab, bosonic systems have bounded energy. Okay, we can define okay the energy observable. It's defined like this. It acts on the tensor product of n Fock states. This is a Wegev vector of the energy operator, and it basically counts the total number of photons. It's also called the total photon number operator. And okay, so what we know, the prior information that we have about our unknown state rho is that it satisfies it's called energy constraint. That the expectation value of the energy operator on rho is upper bounded by unknown constant E dot. That could be, for example, as I said, the energy of the sun, but also, for example, the energy budget that you have in your lab. And okay, we are interested in the scaling with n in the with the number of modes, and so, but this known constant is it scales with n. It's the total energy. Okay. Yeah.
If this is on the energy, then we can reduce this to the finite dimension, right? So the
No, it's not. There exist states that are not finite dimensional.
yeah, but the tail can be truncated, right? Because of we.
I think that's going to be the argument.
Yeah. For example, acquainted states, it has support on. Yeah. So okay, the total energy is extensive. It means that, for example, if you consider the energy of rho tensor n, it's just n times the energy of rho. So this constant scales with n. So we just redefine it by isolating an n here. It's just a definition, just to have that our constant does not scale with n. And so now E has the meaning of average number of photon per mode. Okay, but it's just a definition. So we ask, what is the sample complexity of tomography of an arbitrary n-mode pure state that satisfies an energy constraint? And so this is one of our main results. we determine the sample complexity of tomography of this set of energy constraint states. And so let psi be an unknown state in this energy constraint set. Then a number is of the order of e to the power m over f to the power 2n is both necessary and sufficient to achieve tomography. And okay, this result is informative because it tells us that okay, bosonic tomography is not only inefficient, but we say also extremely inefficient because of this scaling with epsilon. This is different with the finite-dimensional setting, as I showed before. All the scaling, all the epsilon scaling are 1 over epsilon square. Here we have 1 over epsilon to the power of 2n. And this is it's a phenomenon we call the extremely inefficient. The bosonic tomography is extremely inefficient. And because, for example, say that you can solve your problem, for example, for some epsilon. If you want to decrease this epsilon by a factor of 1/2, in the finite-dimensional setting, you don't have to pay much. Here, you have to pay an exponential number of copies more. Okay, so this is one of our main results. Let's see the sketch of the proof of this result. Okay, this is just a standard argument for that has been employed many times in the finite-dimensional setting, and we generalize it to the infinite-dimensional scenario. I will tell you what is the crux of the proof here that differs from the finite-dimensional setting. So let's prove one direction, that any tomography algorithm that achieves the epsilon and delta performance satisfies that the number of copies used are larger than this quantity. So we have the set of n mod states, the blue set, and then we have the set of energy constraint set.
So what does your classical description now look like? Because it's infinite dimensional. Before it was just like a full description of density matrix, it's finite dimensional.
Yeah.
What do you now actually output?
Yeah, it's a finite-dimensional matrix, and you say that okay. I tell you that the classical description is the classical description of a matrix.
Mm-hmm.
Okay, here we have pure state actually with so vectors in a finite-dimensional subspace of the full Hilbert space.
I see.
Okay, so here it is the set of energy constraint states, the orange one, and okay, the argument is the so-called packing net argument, and we select m states, psi1, psi2, psi-m, that lives in these energy constraint states, such that each of them are at least 2 epsilon far apart from each other. Okay, 2 is important here, the factor 2. Epsilon is the trace distance error of the tomography algorithm. And okay, what we did in this proof is to explicitly find these states, psi1, psi2, psi-m, and also m, that depends on the parameter of the problem. So this is the crux of the proof, to find explicitly these states that satisfies the energy constraints. Yeah.
Could you instead not show that they exist by sampling them randomly? So often,
okay,
if you want to show that there's a large set of well-separated states, a random set suffices.
You mean, okay, I'm not, I think that I didn't understand. I haven't understood.
So you say you have an explicit description of the collection of states.
Okay,
Separation.
Yeah, actually we take a superposition between the vacuum and a generic qudit that lives in a big Hilbert space, dimensional Hilbert space. So okay, so this maybe it's what
Yeah, the
word
word generic is I think what I was.
Okay.
Yeah, thanks.
Okay, sure.
And your result is information theoretic. You don't worry about like how difficult it is to implement this measurement, right?
You mean experimentally? Or?
Yeah, because I guess there's like some energy constraint, but maybe to do the measurement you need like the energy of the sun or something.
Yeah, you're right. We're using like trace distance where we don't. Yeah. Actually, yeah, also Jonas some months ago said to me that maybe this is a feature that we are using the trace distance here, that where we are it's the optimal, a bit as the operational meaning as the maximum over all the possible measurements. But maybe it does make sense to, yeah, constrain also the energy of the measurement in some sense. Okay, yeah, and okay, and so the standard argument here is to embed the tomography program in a communication problem between Alice and Bob. So the Alice so select randomly an I between 1 and m, an integer I between 1 and m, and the encoding that she does is that she picks I and produces n copies of psi I tensor n. No, Bob knows the encoding, and his goal is to determine I. So I sends these systems to Bob, and now Bob applies the tomography algorithm, and by assumption, the tomography algorithm provides a classical description of psi tilde that is epsilon close to psi I. So since the psi I are two epsilon parts, Bob can determine with high probability the value of I. So Alice and Bob are able to communicate if the tomography algorithm exists. And now, but we know from O level that if you send a quantum system, you can extract a limited amount of information. You, by sending a qubit, you can extract at least at most 1 bit of information. So, okay, here we are sending a number n small and big number of modes. So we are sending both modes, but we can still apply the Leo bound because we have an energy constraint, and we can show that something like this false. So that the number of state copies in input of the tomography algorithm is lower bounded by basically the number of bits communicated, where m here is the number of messages, but in our framework before it was the size of the packing net. And what we our contribution is to find these sides of the packing net that gives exactly this scaling. Okay. Now the proof sketch of the other direction, the implication is that there is actually a tomography algorithm with the same performances. Okay, and here there is what was proposed before, that you can truncate the Hilbert space with a smaller error if there is an energy constraint. Okay, if there is an energy constraint, basically the unknown state lives approximately in a finite dimensional Hilbert space. And this finite dimensional Hilbert space has a dimension as this dimension. So basically, the set of energy constraint state you can put it with an error epsilon in trace distance in a big Hilbert space of this dimension. So we can. This is the idea of the algorithm. And by exploiting this fact, one can apply the result known for qudit, pure states, and achieves this scaling. And okay, just let's see, let's state this result formally. I said before that actually the effective Hilbert space where energy constrained states lives is this. So we have it is the span of all the Fock states with total photon number bounded by basically the total energy over epsilon squared. And so the result is that if you have a rho that is a state with an energy constraint, then the projection of rho onto the this finite dimensional Hilbert space is epsilon close to the true state. And yeah.
How do you measure the energy of the state?
Sorry?
How is the energy of the state measured?
You mean in lab or in?
No, if I give you, so I'm wondering why this capital E pops up bound. So how is it that related to, so you have a unit vector in this Hilbert space, and how is its energy?
Okay, because you can, the argument is that, you have the trace distance between rho and its projection. Okay, you apply delta measurement lemma. And then, so you have to estimate the probability that qudit measurement, basically the trace between rho and the projector in this Hilbert space. And then here, basically, you can apply Markov inequality that relates the distribution to the mean value over. This is the idea. It comes from Markov inequality, basically.
Denominator epsilon 2n or epsilon 2n plus 2.
You repeat, sorry? Oh, yeah. Here there should be, also epsilon square here. But we are taking the relevant scaling. This is why I'd say I'm using this notation informally. Because we have epsilon to 2n plus 2. But
Yeah, because your effective dimension is like a capital E over epsilon squared. And
you're right. Yeah, but I'm using this notation informates just to say that the scaling is epsilon to the power of n.
I was wondering, like, is there a multiplicative constant inside the exponents or only outside it?
Yeah, actually, there is also a Neper number here.
Okay, there's another number inside the exponents. Okay, thank you.
Yeah, this is this is an informal way to use this theta tilde notation
Okay,
where.
so like okay,
But
That
it is
should be like inside the exponents.
Yeah.
Okay, good.
It's,
So this is the standard epsilon net bound for
You can't get any better
Hilbert
than
space unit sphere, unit ball of a certain dimension, right?
Mhm.
But that's where all these questions are coming from.
Okay, yeah.
Yes, right?
Very much.
I'm a bit confused in your definition of the effective Hilbert space. You say the sum of all these k's should be, I guess, if it's smaller than n times e, I understand why that is, but why should you also divide it by epsilon squared? Because it seems that that's only making the energy bigger, but you can do with just the energy n times e, that would be sufficient.
No, it's not sufficient. It's you have to, in order to get the epsilon error here, you have to take the total photon number scales with like 1 over epsilon square. It's important to avoid that. If you don't put here epsilon the denominator, you don't get this upper bound of the trace distance.
Okay, so you have to include certain states that have too much energy, but you're okay with that.
Because for example, even if the mean energy is 1, the state can have support, for example, on also photon states with 1 billion of photons. It's a requirement on the expected value of the energy, not on we are not like truncating all the photons. For example, in lab, when you turn on a laser, the state is a coherent state. It has a fixed energy, but it has support on all the Hilbert space. But the amplitude of the photons with large number of photons is small. Now we turn to the mixed state case. We don't have a matching lower and upper bound, but here. I just tell you the idea of the upper bound on the sample complexity. The idea it's just that on the structure of energy constrained states, we saw that basically an energy constrained states is approximately a qudit with d equal living in this Hilbert space with this effective dimension. And but we can say something more that actually an energy constraint states has also an effective rank. This effective rank is smaller than the effective dimension of the Hilbert space. So telling this more mathematically, this means that given a state with an energy constraint, it is epsilon close to the state to its projection that lives in this finite-dimensional Hilbert space, and this projection is also close to another state with this effective rank. And so we can basically, this is the idea of the algorithm, that we can apply the result known for the qudit state with rank at most R, and to achieve the performance R times D that we saw in the example 3. And we achieve this performance. And okay, this is what we found on the tomography of energy constraint states. Okay, and we also generalize this to moment constraint states where, for example, you have a prior information not only on the energy, but also, for example, on the variance of the energy of your unknown state, but also for any moment, okay? And we find that the scale, we find the same results. The dependence of epsilon is no more epsilon to the power of n, but is epsilon to the power of n over k. So when k is equal to infinity, you recover the epsilon square case. Okay, but I don't want to go into the detail of this now. And okay, so we saw that there is this phenomenon of extreme inefficiency of quantum state tomography with continuous variable systems. And now we ask if whether there are some relevant class of states for which tomography is efficient. And we show that the answer is yes. For example, for Gaussian states, the answer is yes. And so Gaussian states are states that are most common in lab. Okay, now I define what are Gaussian states, but intuitively they are very common in lab, Gaussian states. And okay, so I already defined the Hilbert space of one mode, one of the Fock states. Then we can define also the annihilation operator. It takes one state with k photons, and it sends it to a state with k minus 1 photons. And from this, we can define the position and the momentum operator. They are observable. We can in lab we can measure it by measuring the amplitudes of the electromagnetic field of the radiation, and they can they are feasible to experimentally measured. Okay, and via the so-called homodyne detection. One puts usually this position and momentum of any mode in a vector called the quadrature operator vector. And this is a vector of operators, R. And now let's give the definition of a Gaussian state. Gaussian rho is said to be a Gaussian state if it can be expressed in this form. It's the exponential of minus beta h normalized. And for some beta, and some quadratic Hamiltonian in the quadrature operator. Quadratic Hamiltonian, I mean something like this. It's a quadratic Hamiltonian in R. And this is relevant. The definition is relevant from the physics point of view because it means that a Gaussian state, it's a Gibbs state of a quadratic Hamiltonian. The Gibbs states are important in physics. And beta has the interpretation of inverse temperature. Okay, and okay, as in classical probability theory, we can define the mean value of your classical probability distribution. Here, it's called the first moment. Is a vector. It's the expectation value of the quadrature vector. And then, as in classical probability theory, we can define the covariance matrix. The quantum covariance matrix is defined like this. Is a generalization of the classical definition. And in classical probability theory, Gaussian distribution are uniquely defined by its its mean vector and its covariance matrix. And also in the quantum setting is like this. If in order to define a Gaussian state, you can it's sufficient to the Gaussian states are in one-to-one correspondence to their first moment and their covariance matrices. So basically, if you know the first moment, the covariance matrix of a Gaussian state, you know the Gaussian state. Okay, and this is a question that is also independent from the topic of quantum state tomography. I think that it is relevant in general for Gaussian quantum information that to answer this question. So it is well known that in order to know a Gaussian state, you have to know the first moment and the second the covariance matrix. But in practice, we have only estimate your first moment and of your covariance matrix. So we don't know exactly the state, and how to measure the error on how to know the state is provided by the trace distance. So it is meaningful to understand what is the trace distance error if you only know the first moment the covariance matrix with epsilon approximation. And this is we can answer this question by finding a bound on the trace distance between two Gaussian states. And you can imagine that rho is the unknown state, rho tilde is your estimate. That first moment the covariance matrix, you can measure it experimentally. It's feasible to do in lab via homodine detection. And so say you measure rho, you measure first moment of the covariance matrix, and you say, okay, your state, it's the Gaussian state rho tilde with first moment the covariance matrix, that the one that you measured. We want to understand what is the error on the state. And we found this bound, this upper bound that relates the trace distance between two Gaussian states in terms of the first, the norm difference between the first moment, the norm difference between their covariance matrices. And the proof of this upper bound is really technical. No standard techniques here works. One could think that one way to prove this is via Fuchs-van der Graaf inequality, and then applying the known formula for the fidelity between two Gaussian states, that it has a closed form. But this strategy does not work because the formula for the fidelity between two Gaussian states is highly complicated, and it involves determinants of square root of both the matrices, and it is at least for us it was really difficult to find from that formula an upper bound like this. Okay, so I just mean that standard techniques to prove this bound does not work, and we exploit some techniques that are called like energy constraint diamond norm of the so-called additive Gaussian noise. Okay, just a detail, and then we found also a lower bound on the trace distance between two Gaussian states, and so we can say that the trace distance error that you make is of the order of square root of n epsilon at most, and at least epsilon over n. And okay, so now with this upper bound, we can now analyze the sample complexity of tomography of Gaussian states, because basically the protocol of tomography of Gaussian state, it's measure the first moment and the covariance matrix. And then in order to get an estimate on the trace distance, you use this upper bound. You propagate the error via this upper bound. And so by using this, basically, we can show that tomography of Gaussian states is efficient. And we found an upper bound of the sample complexity. And that turns out to be polynomial in. And so it is the tomography of Gaussian states is efficient. So the algorithm is the basic one. So just measure first moment covariance matrix. The the crux of the proof is to do the exact the sample complexity analysis, and that the important inequality is this one. This is the main step, and so the algorithm is noise robust in the sense that even if the state is not a Gaussian state, it's a bit far to the set of Gaussian states. The algorithm is efficient. It learns it a sample complexity that is polynomial in N. So we are not requiring actually that the state is Gaussian. It will be also close to the set of Gaussian states. And because, for example, in lab you can have a bit of a dephasing noise that makes the Gaussian states slightly non-Gaussian. And we can improve the sample complexity upper bound for the case of pure Gaussian states. We have another improved upper bound, and so I improved sample complexity. I mean an improved upper bound on the trace distance error, and that leads to an improved sample complexity lower bound, upper bound. Okay, so now we analyze we saw that tomography of Gaussian states is efficient, and now we ask how we want to go beyond Gaussian states, and what we want to see how the efficiency of tomography of Gaussian states is robust by adding some non-Gaussian elements.
Sorry, the main takeaway so far is that like if you have generic states, it's not efficient, but if you have Gaussian states, it's efficient.
Yeah, yeah. And so now we look and discuss of t-dot Gaussian states. So now we will define it. And okay, first let's define what is a Gaussian unitary. A Gaussian unitary is basically a unitary generated by an Hamiltonian that is quadratic in the quadrature operators. And in a lab, it's basically semi-reflective mirrors for the beam splitters, for example. And little fact is that any pure Gaussian state psi is of the form of Gaussian unitary applied to the vacuum of some Gaussian unitary. Okay, this is a Gaussian state psi. Now let's define what is a t-dot Gaussian state. So an n-mode state psi is called t-dot k-local state if it is of the form like this. Basically, you can psi is prepared by applying arbitrary Gaussian unitaries and at most t non-Gaussian gates. And these t non-Gaussian gates are k-mode. Basically, they act at most on k-modes. And okay, this is the set of t-dot k-local states. We are interested in the tomography, the sample complexity of tomography of this. And first, let's tell a result on the structure of these bosonic t-dot states. And here we use a result. We use an extension of a result found a few months ago by Yaroslav and my twin brother in the fermionic setting. And actually, the proof of this result can be also be adapted to the bosonic setting by exploiting the observation that if you take a Gaussian unitary that is energy preserving, the theory of for energy preserving unitary, for a fermionic you have orthogonal matrices that when it's energy preserving, it becomes also symplectic. In the bosonic setting, it's the contrary. Symplectic matrix, when you have that the unitary is energy preserving, becomes orthogonal. And okay, by using this observation, by adapting that proof, one can prove this decomposition that we call compression of non-Gaussianity. Basically, this result means that if you have like a t-dot circuit, you can by applying another Gaussian unitary, here you can compress all the non-Gaussianity on the first modes, and on the first KT modes via a suitable Gaussian unitary G. So this is the composition. And so any T-dot K local state can be written in this form. And okay, actually, this is also an analogous result. There is also in the Clifford setting where you have stabilizer states and, instead of Gaussian states, and non-Clifford operation instead of non-Gaussian operations. Yeah.
Sorry, in a finite dimensional quantum system like you have here now, how does it look like a Gaussian unitary?
Can you repeat? Sorry.
Yeah, a Gaussian unitary. How
Yeah.
does it look like in a finite dimensional system like here?
This is not a finite dimensional system.
Well, you have n qubits, right?
Oh, n modes. This is the vacuum. Okay. This is the vacuum, and I am applying a non-Gaussian unitary, and here a Gaussian unitary. This is we are still in the Hilbert space of n modes.
And what's the definition of a Gaussian unitary?
The definition of Gaussian unitary is unitary that G that can be expressed that is generated by a Hamiltonian that is quadratic in the quadrature operators.
Okay.
And yeah, it acts nicely on the in the Heisenberg picture on the quadrature operator via so-called symplectic matrix. So basically, it is identified by this symplectic matrix that acts on only. It's just a 2n times 2n matrix.
Like can you repeat what the quadrature was again?
You repeat, sorry?
For the Gaussian unitary, I was confused about that. Can you just repeat what the
The definition of Gaussian unitary?
Quadrature.
The definition of quadrature. Quadrature operators are these vector R that are related. It is defined like this. You put in the vector all the position and momentum of all the n modes of your bosonic systems.
And then for each, it's like e to the power I h, and it's quadratic.
Yeah, for a beam splitter, you have a quadratic Hamiltonian that is in terms of these quadrature operators.
Written out matrix.
Sorry, I
Like, I
cannot
was
listen.
thought it was just not just to the power of 1, but then I think I have to look at it.
Okay, yeah, we can explicitly express the unitary of a beam splitter in terms of an Hamiltonian that is quadratic on the position and momentum of the modes. Yeah. So, okay, I was just saying that in the also this is a result known in the Clifford setting, and both in the fermionic, so in the finite dimensional setting, both in the fermionic and in the Clifford, this analysis of tomography of this class of states has been done, and yeah, we are now extending this result to the framework of bosonic systems, infinite dimensional systems, and so we ask how can we do tomography of T-dot states, and by having this decomposition, the tomography is simple because intuitively by estimating the first moment and the covariance matrix of this state, you can learn what is G. Yeah.
Is the Gaussian part also time efficient to like do the estimate, to write the estimate?
Yeah, because you have to measure the first moment the covariance matrix, and time efficient is the polynomial, and then you have to put the covariance matrix in so-called Williamson decomposition, and this is also efficient. It's polynomial. So you can basically learn G. After you learn G, when you run the experiment on the copies that you produce, you apply to the copies G dagger, and so you undo G, and so basically on the remaining copies you can you have just a state on 80 modes, and then you have approximately also the vacuum here. So now one can just do full state tomography on the first two KT modes to have a classical description also of this state here. And so you know these states with on KT modes, and you know also the unitary. So you putting these together, you have an approximation of your T-dot state. And in order to do the sample complexity analysis, there are some technicalities here that I am omitting, like the energy how it involves here, because you have to propagate the energy here in order to have guarantees on the full state tomography. You have to find an upper bound of this, the energy of the state. Okay, but here I don't want to go into details with this. I want just to tell you that if KT is of the order of 1, but does not scale with n, then tomography of T-dot K local states is efficient, meaning that we can go a bit beyond the set of Gaussian states and still have the tomography is efficient.
Is logarithmic and also works, yes, or no?
Can you repeat?
Is logarithmic it also is efficient or no?
No, because this is a difference with the finite dimensional setting, because here you have also the energy that comes into play. And here, the energy of the states, the total energy is this is dependent with n. So you have like the sample complexity.
Your full state tomography is much worse.
Yeah,
Is that the problem?
Sorry?
That your tomography algorithm is much worse than in the finite dimensional case?
Okay, no, I think that it's not that, but it's like that in the sample complexity of tomography, it tenders the energy.
Yeah.
And it's like energy over epsilon square to the power of KT.
Yeah.
But the energy of this state turns out to be linear in n. For example, if you have a T-dot state also already in this form, you can concentrate the energy of all these n-mode states here, and this depends on n. So here, this energy is it's linear. The energy of the state phi depends on n.
So you end up with an extremely high energy state.
Yeah, you can put all the energy of the n state here, and so it's basically a behavior like n to the power of KT. So when KT is logarithmic in n, you have a super polynomial scaling, still not exponential, but not polynomial. And this is okay. We also found the lower bound of the sample complexity of compressible states like this, and so this is by doing exploiting this compression, this scaling is optimal.
Yeah, another question. Like I've heard of Gaussian states, and I know that they are kind of natural and stuff. But like this construction, the T-dot K local states, how natural are they? Is it like something that is well known, or is it just something that you came up with for that thing?
Yeah, it's okay. I think that they are just theoretically interesting. I don't know. Maybe also okay. If you want to give some maybe some experimental explanation of this, I think that you can come up with some examples. For example, I don't know.
Is that something that was already like in the literature, or is something that you introduced?
Yeah, we introduce.
Well, by analogy, right?
By analogy.
A little bit fair to you, because this is sort of a natural object. If you think about extended stabilizer states, it's sort of things that are composed of circuits of Cliffords and T states, T gates. Then you can do it with fermions. That's what Yaroslav did, and they now did it for bosons. So it's sort of a natural theoretical construct. It's also the area in which you can usually prove things, because you have a lot of algebraic structure that you don't get if you just put a sort of non-Gaussianity constraint.
I mean, I guess the additional thing is that, like together with the non-Gaussian gates, I mean, at least in the finite dimensional setting, it's the gates that becomes universal. I'm not sure if it's the case here.
Yeah.
So do you sort of get just one non-Gaussian thing and suddenly becomes universal, I guess, or?
Yeah, that, yes.
Yeah, so and then also, but then if you have only a finite number of these sort of non-Gaussian gates, then I guess it's also classically simulable, is it?
Yeah. If you this is not done. Okay, this was
I think it's not that easy.
Oh, okay. Okay, this was one of the
Wasn't this recent work by Diaz and Koenig now?
Yeah, you're right.
On bosons.
Yeah, I contacted the authors a few weeks ago to ask exactly this question. But this is not this is not trivial. While in the fermionic setting, their result implies also simulability of T-dot. In the case of bosonic, it's not trivial
Because like a gate injection, it doesn't work directly or something.
Yeah, their result that does not imply that this circuit is classical simulable. Does not imply this. So it's an open problem if this circuit is classically simulable or not.
Okay. I have another question about your algorithm. You sort of compress to the zero state.
Sorry.
So in the algorithm, what you do is you sort of identify a transformation that compresses you to sort of compresses everything into the small subspace.
Yes.
And it has the vacuum everywhere else.
Yeah.
And then you run into this sort of tomographic problem.
Mhm.
But in principle, you could sort of compress to a known Gaussian state, right? That still has some energy. So maybe you can avoid the energy problem. Is there like a real lower bound? Is there a matching lower bound? I think is my question.
Okay, I'm not sure I'm understanding. Sorry.
So in these algorithms,
Yes.
sort of analogizing from the stabilizer case, you go to state tensor 0 because it's convenient, but really only the tensor is important because you could go to state tensor known stabilizer state, or in this case, known Gaussian state, and that would also work. You have to do a different transformation, but it'd still be possible. And then, in this case, in the stabilizer case, it doesn't matter because there's no energy, but here there's energy. So you might want to like put as much of the energy as you can in that Gaussian state on the other side. Because here your problem is sort of that you're squeezing all of the energy into this one state, but you don't have to.
But then you have to learn also the state that it's here.
It doesn't matter, right? It's going to be a known Gaussian state. No one's stopping me from changing the compression transformation
Okay, you see.
to map to phi tensor some fixed Gaussian state, like
I see. Then
a superposition over a
you-
fixed number of modes that has some fixed energy. Yeah.
And
Because
so-
Gaussians act transitively on Gaussian states, so you can pick whatever you want there.
Yeah, so you put there.
It's not obvious that you can actually show that the energy can be moved, right? It's not obvious that.
Yeah. It's not entirely obvious, but like there's no a priori reason why you should pick the vacuum there.
Yeah, basically saying there is extra degree of freedom with this. Or
Yes,
didn't
yeah,
deploy it.
that might help.
Yeah, you're right. Yeah,
Yeah.
it could be an idea to improve the scaling to prove.
I mean, because you,
It's,
like earlier, you said you had a matching lower bound, or was that not?
I mean, we have a matching lower bound for the class of compressible states. We define compressible states as are the states that are
They're bigger
in
than
this,
T-dot.
in this
Yeah,
form.
yeah.
That they are bigger than T-dot. T-dot are compressible states.
Yeah.
Compressible, I mean, just that are in this form.
But to be fair, I mean, if it is the case that the state is decompressible in this form, if a state can be compressed in Jonas form, it will also be compressed in this form, right?
Yes, because you
yeah.
can just add arbitrary
yeah.
Gaussians in the back.
Yeah, yes. So it's this idea should not.
I guess the point is that the Gaussian operation is not necessarily energy preserving.
Yeah, but okay,
Yeah.
here we are, no, it's not energy
Yeah,
preserving.
I guess that's the
Yeah,
problem.
here we have an assumption that the state psi has an energy constraint.
Yeah,
So-
do you assume that the G has to be energy preserving
No,
for the
we-
compressibility? No. we don't.
We are assuming that the state psi, the total state psi has energy bounded.
But G does not
G
have to be
can-
preserved.
No, G is
General Gaussian.
a general Gaussian. Yeah, such that of course the total energy is at most the upper bound. Yeah. So okay, maybe if you define like this class of states where you put a pure state here, you can put the Gaussian here.
Yeah, it's not clear. Yeah.
But but I think that it does not change. It's the following.
Your conclusion will hold. So I think my idea is just doesn't work.
Yeah, because we are requiring that the energy are an assumption of the total energy of the state, not on the structure. Okay. So this is the conclusion. So in our work, we tried the first investigation of tomography of bosonic systems with rigorous performance guarantees, and with respect to trace distance. This is important because in experimentalists, when do tomography of bosonic states, they usually like approximate the so-called phase space function, like Wigner function or stuff like this. We don't do approximation on the phase space case, but we have guarantees on trace distance error.
People probably have rigorous guarantees for like the correlation matrix directly because that is very direct, right? So people do have guarantees on something.
Yeah.
So that's some like I mean, it's just like it's not that the phase space. Do people have guarantees on the, for example, on the Wigner function that it's?
No, I don't know any result that it says that you need this number of copies to get an L2 error on the Wigner function with.
For covariance matrix is pretty straightforward.
Yeah,
right?
for covariance matrix, yes, but covariance matrix that uniquely define the states only if this is Gaussian. But then you ask.
But the observables, for example, would follow. So like if you have like something that's expressed in covariance matrix, some like some like first moments of some operators or whatever, x squared, x fourth, it will be expressed in terms of the covariance matrix if it's a Gaussian state. And therefore an error, somehow bounded error in covariance matrix would imply a bounded error in the observable. Maybe that's just what experimentalists care about directly. So I just wonder if anybody sort of did that analysis for the sort of more simple, not trace distance, but rather.
Okay. Yeah. Maybe. Maybe yes. It's in the for technological purpose. Maybe one is interested more in.
I guess the practical point is that I'm not sure if you already put out this paper, but when optical people read this statement that like the sentence as it's written right now, maybe if they're like these weathered quantum optics people from the 80s, they're like, well, I mean, of course, everybody knows that the covariance matrix is approximated accurately, and we have the guarantees on that. We just never wrote it because it's so obvious. But I mean, to be fair, it is obvious. It's not obvious for the trace distance. It is obvious for covariance.
Yeah, maybe I should add with respect trace distance and yeah, because actually it's simple the observation that if you have an energy constraint, then you can derive exactly guarantees on the estimation of the covariance matrix.
There is an energy constraint, so that's not entirely trivial, I guess. But you say it's pretty obvious. So.
You have to apply like Chebyshev,
right.
or something that to relate the elements of the covariance matrix to the energy operator. But yeah, it's.
I mean, you can decide yourself how you're gonna market it, but like if you write it the way that's written right now, it can sort of raise some criticism because of it.
Yeah, I agree with you. Yeah,
the optics people will never read it anyway.
They should. I mean, they should read it and cite it as whatever. Read the paper. No, it's
yeah. Sorry. Hi. Sorry. Can I ask something which probably was asked implicitly in some of the questions? So some of the results, they are derived under the assumption that you have, for example, the guarantees for the Gaussian state, that you assume that you have a Gaussian state to start with, right? But in experiment, if I measure first and second moments and I stop there, I have no idea what the state looks like. I can only think, right? I can like evaluate the trace distance, etc. It's a statement about first and second moments, but it doesn't tell me, I can have very complicated non-Gaussian state. If I only look at first and second moments, I have no idea what the state look like. So is this true actually, or how do you have some comments on like non-Gaussianities in this sense?
Okay, you are saying that how do you know if a state is Gaussian or not?
Well, the statement is I cannot tell if I am only looking at first and second moments.
Okay, I think that maybe in some experimental situation you are using maybe only laser and mirrors, stuff like that. So you know that since since of the of the element that you are using in your experiment, that you expect a Gaussian state in the output, and maybe there can be a bit of imperfections, like the phasing puts a bit far away from the set of Gaussian states. But I'm thinking about a framework where you have the prior assumption that your state is Gaussian, and then it's the first moment the covariance matrix suffices. Yeah, okay. Otherwise, one would also ask property testing of Gaussian states. So if you have an unknown state rho, you want to answer the question: it is the state Gaussian, or maybe it is epsilon far to be a Gaussian state. And after solving this preliminary problem, then you decide whether or not the state is Gaussian or not. but also still this one is an open problem in this bosonic setting, how to derive sample complexity of property testing of bosonic case. So one can do maybe a preliminary step of property testing and then actually do tomography.
Okay, this was my question essentially. Okay, thank you.
Yeah.
You said your algorithm was efficient, but then the powers of the polynomial were like 4 and 7.
Okay.
So do you know how much room there is for improvement?
Okay. I don't expect that this is the optimal sample complexity. With the analogy with the fermionic setting, where I think that the sample complexity of Gaussian states is has been found the optimal one, right? I think that one can improve from with the analogy of the fermionic setting, because I know the sample complexity upper bound in the fermionic setting that should be optimal. I think that one can improve from 9 to the power of 7 to the 9 of the power of 5th. Here, because basically here we have e to the power of 4, that is the energy per mode. So if you put, it's like n to the power of 3 times the total energy to the power of 4. And for fermionic case, the total energy is fixed, thus dot scales with n. And the fermionic setting, I think that the optimal scaling is linear in n, right? So this is why I think that one can improve of a factor 2.
Yes.
Does it make sense to compare with stabilizer states?
I think that it makes more sense to compare with the fermionic states because there is more analogy. Yeah, but also with stabilizer states, like from a resource theory point of view, but for example, here Gaussian states are a continuous set of states. So I mean, I think that the analogy that makes more sense for fermionic case if you want to compare with finite-dimensional systems. And so to conclude, we found sample complexity bounds for energy constrained states and the moment constrained states. We found the optimality for pure states, the relevant scaling. And we found this phenomenon of extreme inefficiency of bosonic tomography due to the scaling with the trace distance and the number of modes. And then we delved into the analysis of tomography of Gaussian states and t-dot Gaussian states that I will show that is efficient. And we provide some tools that can be maybe of independent interest, that are these bounds on the trace distance between Gaussian states, simple bounds. For example, not like the fidelity bounds that is highly complicated, but simple bounds in terms of the norm difference of the covariance matrices. And we also these notions of effective rank of energy constrained states or moment constrained states, and also this decomposition of dot Gaussian unitary states, Gaussian unitary and states. And there is a list of open problems that, for example, to determine the optimal sample complexity for the mixed case, also the optimal sample complexity for Gaussian states, and maybe also property testing of Gaussian states, deciding whether a state is Gaussian or epsilon power to be Gaussian. And then also one can ask the same thing for bosonic channels. So tomography of arbitrary bosonic channel, maybe with respect to the energy constraint diamond norm, or also tomography of bosonic Gaussian channels. Okay, thank you.